Hello and welcome to the Introduction to Multiple Regression module. In this module, I will demonstrate regression techniques that are intended for analyses when the dependent variable is a scale or synonymously a continuous dependent variable. In this module, we will begin with basic regression concepts, including showing the equivalence of regression to other statistical methods. I will also demonstrate how to code and center variables for analysis. We will quickly then move into multiple regression, where the discussion will include testing of required assumptions, testing for multiclinearity issues, the effects of using covariates. I will also distinguish between main and interaction effects in regression, and throughout I will focus on helping you correctly interpret the intercepts and slopes from a regression output. The data file that I'll use in this regression module is in SPSS format. SPSS has multiple file formats, but we know this is a data file in SPSS format because it has the file name extension .sav. Before beginning, I wanted to note that the data file is for educational purposes only, and that is because that some of the variables in the data file contain simulated data. So any of the statistical results that might come from analyzing the data should not be interpreted outside of the educational purposes of learning regression for the course. The data file has a few highlights that I'd like to point out to you. The data file is structured, it has 30 students in the data file, and for each of those 30 students, we have several variables containing information about those students. We have a course final exam score. We also have a pre-course score, which is their score on the final exam administered prior to the course, so it functions like a pre-test. We also have the student's department affiliation, their race, their sex, their comfort with statistics, whether or not they participated in tutoring, and whether or not they completed key course assignments such as the study questions assignment. I'd like to begin with a review of scales of measurement. The first type of variable I'd like to talk about is the categorical, discrete, or nominal variable. In statistics, we often use numbers in these variables, but those numbers do not have any numerical or quantitative properties. They are merely used to distinguish people into different categories or groups, such as membership in the College of Business or membership in the College of Education. The second type of variable that I'd like to discuss is the ordinal or the rank variable, and here the numbers are used to indicate ordered levels from lowest to highest. For example, a Likert scale from strongly disagree to strongly agree. And then finally, I want to mention the continuous interval or scale type of variable, where we make the assumption that the intervals between the levels are equal in size. So an example would be test scores. And here, with the continuous variable, the mean or the arithmetic average of these variables is highly interpretable, where it is not so for the categorical or ordinal variables. I'd like to pause here and just provide a reminder around terminology. And that is because measurement levels have several synonyms. So as you saw on the last slide, categorical, discrete, and nominal are all referring to the same type of variable. But I'm flagging it here because often I will use the term categorical, whereas SPSS will use the term nominal. Similarly, within the larger category of categorical variables, you may see people refer to a variable as binary or dichotomous, but those mean the same thing. It just means that there are two categories or two levels to that variable. And then finally, I wanted to flag that although I will often use the word continuous in reference to a variable, that means the same as an interval variable or a scale variable. And again, I'm bringing this to your attention because SPSS uses the term scale, but it's just synonymous with continuous. When you open up your SPSS data file, you should see something like what's on the screen right now. And I'm noting here with my red circle that we have 30 rows or 30 cases corresponding to the 30 students in this data file. The other thing I want to note is that you see down below that data view is in gold. That's just indicating that right now we are looking at SPSS in the data view. But coming up in the next slide, we're going to look at another way of looking at these data, which is the variable view. Once over in the variable view, we can see that we have 39 different variables or pieces of information about the 30 students. And I've highlighted in gold this label column in the variable view, where you see for each variable I've provided the coding for those variables. So this label column functions like a code book for this data set. Also, in the other red circle, you see the 3 dots. If you click on those 3 dots, you can see additional information for how that variable is coded. So if you click on the 3 dots for the questions variable, as indicated in the gold cell with the red circle, you'll get a pop-up box called Value Labels, where you can see additional information for how this variable is coded. 0 for did not complete the study questions, 1 for did complete the study questions. And that information should be consistent with what is in the label column for this variable. Before doing any regression analyses on these data, I always encourage students to first look at overall and disaggregated descriptive statistics for the data set. On this particular slide, I have some tables that represent both overall and disaggregated descriptive statistics, and I'll show you later on in the module how to ask SPSS to give you these data. But just as a high-level look, we can see in the red circle, for example, that the average pre-score for the students was 77.20, and that's about 7 points less than the average final score for those students, 84.20. So that's an example of looking at some overall descriptive statistics. If we wanted to look at some disaggregated descriptive statistics, we might look at, for example, the 2 numbers between the blue bracket there, where we can see differences in final score averages for students who did not do the tutoring, who are coded 0. And we see that their average score for the non-tutoring students was just under 79. Whereas for the students who have a 1 for tutoring, which means they attended the tutoring, their average score was 89.5. Having noticed a few patterns in the descriptive statistics, and certainly we could spend more time looking at those descriptive statistics, and we will later on in this module, let's now move on to simple bivariate regression. And what I mean by bivariate is that means 2 variables. And indeed, those 2 variables are a single independent variable and a single dependent variable. And the goal in the simple regression is to try to express the strength of relationship between that single independent variable and the dependent variable. And we do so by examining the slope of the best fitting line through a series of points. And by best fitting, we mean the line that lies closest to all the points in a bivariate scatter plot. And we see in this graph that while there are many ways to draw lines through any set of points, statistically speaking, there is one and only one line that best fits these data. Let's take a few minutes and ask SPSS to make a scatter plot for us, similar to the one we saw on the previous slide. In your data view within SPSS, you'd want to click on Graphs and then Chart Builder. Once in the Chart Builder menu, you'll want to click on Scatter/Dot, and then you see the first option for scatter plots there on the far left. And the scatter plot option should show up in the white preview window as well. Once you've identified the scatter plot option, the next step is to identify the variables and where you want to plot them. So for example, final score, I'm going to click on that and drag it to my y-axis. And pre-score, I'll click on that and drag it to the x-axis. Once you have moved the variables of interest onto their desired axes, you'll get a preview of the scatter plot. Note that this is not an accurate scatter plot, it's just a preview, at which point you can say OK, and you'll be ready to generate your scatter plot. Once you say OK in the Chart Builder menu, you should see in your SPSS output file a scatter plot that looks like this. I'm not going to unpack this scatter plot at this moment on this slide. I want to first talk a little bit about the algebraic form of this line that we're looking at, and then we'll reconnect it to this graphical display. Let's talk a little bit about the general algebraic form of the regression line, like the one we saw in the previous slide. You may recall from high school algebra, y equal b plus mx, where that is the equation of a line where b is the y-intercept, the place where the line crosses the y-axis, and m is the slope of the line. In high school algebra, we refer to this as the slope-intercept form of a line. Well, in statistics, we use a very similar approach. We just change the symbols a little bit, where the b in the top equation is the b0 in the bottom, and the m, or the slope of the top equation, is just represented by b1 in the lower equation. Specifically, y in the second equation is the value of the dependent variable. x1 is the raw score for the independent variable. The b1 coefficient is the slope of the line. The b0 is the y-intercept. And the e represents the errors in the model prediction, or also called the residuals. So we could take the second equation, y equals b0 plus b1 x1 plus e, and just convert that into something that looks like what you'd use in a study, where you have a dependent variable on the left, and you're modeling that as a function of some independent variable on the right. One other thing that I want to point out is that a general principle in regression modeling, a kind of simple way to think about things, is that your actual data, your raw data, is some combination of what the model would predict your data would be, plus the error that resides between your actual data and what the model would predict your data to be. So in thinking about this particular second equation, if the y is your dependent variable data, then the model is your slope and your intercept, what's in the red rectangle there. And then any differences between your actual data y and what your model would predict, which is in the red box, is the error that's on the far right. Let's return to our scatter plot and use it to connect to some of the concepts from the previous slide. For example, I have circled in red one case or one data point in our scatter plot. And we can see that that point isn't exactly on the line, which means that the model, which is represented by the line, doesn't perfectly predict that data point or that dependent variable value. And if we wanted to know exactly the difference, we would subtract from the data point, which is y, we would subtract its predicted value, y hat, which is the value on the line directly above it, and then the difference between the actual value and the value of on the line directly above it is the error or the residual. And we can do that for another data point elsewhere in the scatter plot using the same logic, where we look at that distance between what the model would predict, which is where the line resides, and the actual data, which is where the point resides, and look at that difference between those as the error or residual. We can also notice that the line, when extended backwards, goes almost through the origin. So that tells us that the y-intercept is approximately 0. We can also try to look at the slope of the line by identifying a horizontal run and a vertical rise. So the first bracket I've put on the graph here is a horizontal run, which looks like it goes from on the x-axis from 20 to about 90. So we're expecting that run to be about 70 points. And across that run, we can identify how far the graph rises, right? And I'm now putting, as you can see, dotted horizontal lines over to the y-axis so that I can identify the actual size of that rise over that run. And it looks like that rise is about 80 points over that 70-point horizontal run. So using rise over run as our definition of slope, we see that the B1 slope is about 1.1. Well, we now have identified just graphically two parameters of the regression equation that we can use to customize this very general regression equation that's at the bottom of the slide. So now, instead of just having dependent variable, we can customize that to say final score is equal to the y-intercept, which is approximately 0, plus the slope times the pre-score, where the pre-score is our independent variable. And we can substitute in 1.1 for that B1 slope. And now we have a customized equation for this particular regression relationship. Let's take this notion of data equal model plus error, and let's apply it again looking at our scatter plot in the context of predicting someone's final score from knowledge of their pre-score. Say, for example, that we were interested in predicting someone's final score value knowing that their pre-score value was 67. To obtain their predicted final score from just knowledge of their pre-score, we could go up to the line here and over to the y-axis and see that their predicted final score is in the low 70s. But we also see that we have some people in this scatter plot who had a pre-score of 67, whose actual dependent variable score, final score, is quite a bit larger than the low 70s. In particular, this person who I've circled in red, if you extend them over to the vertical axis, the y-axis, you see that their actual value is nearly 90. It's in the high 80s. And that the blue bracket here is the difference between their actual final score and their predicted final score. And that appears to be about 14 points. So if we return to the data equals model plus error concept, and we bring from the previous slide our customized equation for this relationship, where final score equals 0 plus 1.1 pre-score plus error, we can identify in the red rectangle that the 0 plus 1.1 pre-score is the model part of this relationship. And of course, as we just saw by the distance between the actual point and the predicted value, that there is error in this prediction. So plugging in some numbers, we can take this the next step and say, okay, final score is equal to 0 plus 1.1 times 67, because that is the pretest score of interest. And when we plug those numbers in, we get 1.1 times 67 plus the error of about 14 points. And we can conclude that this person's final score can be estimated by knowing what the model predicts, which is the 0 plus 1.1 times their pretest score, plus what we know the error to be, which is about 14 points, and we can arrive at their actual data point of 87.7. So the purpose of this slide is just to do a little bit more conceptually in terms of the decomposition of the data into a model part and an error part, where 87.7 is the actual data for this person. 73.7 is the model-based prediction of what their dependent variable value would be. And 14 is the error or the difference between what the data actually are and what the model would predict. Okay, let's take our first stab at interpreting regression elements. As you can see on the slide, I have our regression equation in terms of the dependent variable and independent variable. And I'd like to look at the intercept and the coefficients separately and do so with both a graphical and a statistical interpretation. So what we've seen so far looking at the scatter plot is that the intercept B0 is the place where the scatter plot regression line crosses the y-axis. And statistically, you can also think of it as the estimated mean of the dependent variable for when the independent variable is 0. For the coefficients, we can do the same. Graphically, we saw that in a simple regression, the single coefficient B1 is the slope of that scatter plot line. Statistically, the analog would be that the coefficient is the estimated change in the dependent variable for 1 unit increase in the independent variable. And then we can take it a step further and look at our customized example where we had final score equaling an intercept of approximately 0 plus a slope of approximately 1.1 times the pre-score plus error. And what we can infer from that is that for students with a pre-test score of 0, our estimated post-test score will be approximately 0. And that for every 1 point increase in the pre-score, we're estimating the final score to increase by 1.1 points, and that came from us naked eye estimating the rise over the run of that scatter plot line, 80 over 70, and of course that reduces to 1.1 over 1. Now let's take a minute and ask SPSS to run this regression model for us. We'll do that by accessing the Analyze menu, pulling down to Regression, and then pulling over to Linear. Once in the linear regression menu, you can see that there is a list of available variables in the left-hand box. I'm going to choose my desired final score as my dependent variable and use the right-hand arrow to move it over into the dependent variable box. And if you have moved final score successfully over into the dependent variable box, it will show up here in gold. And once you have final score identified as your dependent variable, you can use a similar process, identifying pre-score and moving it over using the right-hand arrow button into the independent variable box. And once both your independent and dependent variables have been identified and moved into their appropriate boxes, then we want to click on our Statistics button to make sure we get all the statistics we want to come out with our regression output. After clicking Statistics, you'll get a linear regression statistics box. And you'll want to go ahead and check all the boxes that I have checked here in this particular window, including estimates, confidence intervals, model fit, part and partial correlations, and collinearity diagnostics. Then click Continue. After clicking Continue, you should return to this linear regression box, at which point you can click OK and generate our first regression output. So once you've run the regression in SPSS, you'll get several tables in your SPSS regression output. I've grabbed a couple of the most relevant here to put on the slide, and that's the model summary table and the coefficients table. And what I want to do is I want to draw some comparisons to what we observed in the scatter plot on previous slides and what the regression output is telling us. So let's start again with our generalized form of the regression line in terms of dependent variable and independent variable, and then the customized version in terms of final score and pre-score. Note that down in the coefficients table, I inserted a B0 there, and that was just to mark for you that in SPSS, the coefficients tables from regression runs do not refer to the intercept as such. They call the intercept the constant. So when you see the constant row in any SPSS regression coefficients table, that really is your intercepts row of the table. And I denoted that with a B0. Similarly, just for clarity, I put a B1 next to pre-score because that corresponds to the slope in front of the pre-score independent variable. So in the coefficients table for SPSS, you see there's an unstandardized coefficients section, and then there's a B column. So that's where your intercept and your one or more slopes, those values will be in that column. And all I've done there is just give the different estimates a subscript of either 0 or 1. In terms of their values, note that the estimated value of the intercept is 0.203, which is pretty small. And that is consistent with what we, just naked eye, looking at the scatter plot, we estimated that the intercept was about 0. So this is consistent with the graphical interpretation and the formalized output from SPSS. Similarly, SPSS is estimating that slope of that line to be 1.088, which is consistent with what we estimated naked eye from the graph, just looking at the rise over the run. One other thing that is provided in the coefficients table that obviously you wouldn't know just from inspecting the scatter plot is the statistical significance of any of the effects that are in the regression model. What the circled value of 0.000 is saying is that there's a very low probability of a type 1 error. The significance column in your coefficients table are essentially your p-values. And by rights, that should be reported as less than 0.001. But be that as it may, this small value for the p-value is certainly less than 0.05, so that is suggesting that the relationship between pre-score and final score is statistically significant. And while we're on this topic, just like in many other statistical tests, in regression you have a null and an alternative hypothesis. And the null hypothesis in regression is that your intercept and your slopes, B1 all the way out to B to the n, how many ever variables you have in your model, that all of those intercepts or slopes are equal to 0. So in this case, we would reject the null hypothesis that the pre-score effect is equal to 0. One other thing I want to point out comes from the model summary table, and that's the R-square value. This is sometimes referred to as the coefficient of determination. But the interpretation of this R-square value is that 81% of the variance in the final score is explained by the pre-score. And we often use the R-square as a way of knowing whether we have a predictive or explanatory model. Before moving on, I would like to take some time to help bridge the gap between more basic statistical approaches and regression. So I'll do that by showing the equivalence of regression to some of our more familiar statistical methods that we learn about in basic statistics classes. For example, one thing that I would like to demonstrate is that linear regression really comes from the same parent framework as other familiar statistical methods. And some of those methods might include the t-test, the Pearson R correlation. And that parent framework is called the general linear model. So what I'm planning to demonstrate is that we can specify regressions in such a way as to produce the very same estimates or inferential conclusions as seemingly different, but really the same statistical techniques. So let's start by talking about the equivalence of regression to the Pearson R correlation. Regressions can address some of the same types of questions as correlational analysis do. In particular, what's the strength of a relationship between a continuous independent variable and a continuous dependent variable? As it turns out, simple regression will give you the same results as the Pearson R correlation, provided that the raw scores are first standardized as z-scores before regressed on one another. Recall that to get a z-score equivalent of a raw score, you take the raw score, which I have as value in this expression here, you take the raw value, you subtract from it the mean of those values, and then you divide that difference by the standard deviation of those values. So kind of simply put, if we want the Pearson R correlation between, let's say, final score and pre-score, we can grab the B1 coefficient or slope from a regression model that regresses the z-score equivalent of the final scores on the z-score equivalent of the pre-scores as shown in this regression model. Let's go ahead and make comparisons between the Pearson R correlation and a corresponding regression using z-scores. On this slide, I'm showing you how to go ahead and get the Pearson R correlation. Within SPSS, you'll want to start with the Analyze menu and pull down to Correlate and then Bivariate. And then once in the Bivariate Correlations menu, you'll want to start by selecting Final Score and Pre-Score, which are our variables of interest, and use the right-hand arrow button to move those variables into the Variables box. And then before proceeding, making sure that you have the Pearson and the two-tailed options checked. And once you've done that, your bivariate correlations window should look like what we have on the slide here. And you can proceed by selecting OK. And once you select OK, you should have correlation results in your SPSS output file. I've grabbed the correlations table from the output and pasted it on this slide. And we can see that the correlation between pre-score and final score is 0.90. That shows up in two places in the box. And the 2 stars indicates that the correlation is significant at the 0.01 level. That corresponds to this significance row in the table, which is really just your p-value, probability of type 1 error. And again, these really ought to be reported as less than 0.001. But big picture, we're seeing a pretty strong correlation between pre-score and final score, and it is statistically significant. And just as a reminder from a few slides ago, the parallel regression analysis to the Pearson R correlation is to regress the z-score equivalent of final score, regress that on the z-score equivalent of pre-score, and then identify that B1 slope from that regression model and compare that to the Pearson R correlation we just estimated. So to run this regression, I'm going to use my similar Analyze linear regression menu. And once inside the linear regression box, notice how I have moved the final score z into the dependent variable box and pre-score z into the independent variable box, and you'll see those variables are in your data file. So I've moved those variables into their appropriate boxes, and I'm just going to click OK and run the regression. And then grabbing the coefficients table from the regression we just ran, we see that the unstandardized coefficient for pre-score there is 0.900, which of course maps exactly onto the Pearson R correlation that we ran just a few minutes ago. Now let's spend a few minutes showing the equivalence of regression to the t-test. As it turns out, regression can also address questions related to the mean differences between groups, which is what typically t-tests have been used to address. In fact, a simple one independent variable regression will give the same statistical conclusions as the independent samples t-test. Said more specifically, a t-test between final score and tutoring no tutoring will have the same statistical conclusion as testing the slope of a regression where we regress final score on tutoring, where tutoring is a binary categorical variable coded 1 if the student attended and 0 if they did not attend. To show the equivalence, let's first run a t-test of final score versus tutoring. And we can do that through the Analyze, Compare Means, and Independent Samples t-test menus. Then, once inside the Independent Samples t-test menu, I would first migrate final score over into my test variable box, and then identify the tutoring variable and use the right-hand arrow button to move it into my grouping variable box. And once tutoring is entered into my grouping variable box, I then need to define the groups. And within the Define Groups box, notice that I've given Group 1 a code of 1 and Group 2 a code of 0, and then click Continue. And then once back in the Independent Samples t-test window, you can see under Grouping Variable that my new coding of the tutoring variable is present there, 1, 0, and I'm ready to click OK. Let's look at the t-test output. I've grabbed the primary independent samples t-test table and put it here on the slide. I'm going to bring your attention to the estimate of the t-statistic, 2.207, and the statistical significance of that test. So that's saying there that the p-value is 0.036, which is statistically significant. Also of note is that the independent samples t-test output gives you the mean difference between the two levels of your categorical independent variable. So that's saying that the mean difference in final score is 10.53 points, which means that the students who did the tutoring on average scored 10.53 points better than the students who did not do tutoring. Now, equivalently, we could quickly run the regression of final score on tutoring and see what results we get. So here's just a quick screenshot. All I did here was do our normal process of running regressions. It's small, but you can see in the box that I've regressed final score on, as the dependent variable on tutoring as the independent variable. And here's the coefficients table from that regression run. Note that I get the same exact t-test estimate, statistic, and I get the same p-value, 0.036, and the unstandardized coefficient, the B1 of that model, is actually giving me the mean difference in final score across the two groups, tutoring and no tutoring. Let's look at our regression model graphically. So I put a dotted line here on this scatter plot of final score versus tutoring, just to indicate that this is the vertical line that corresponds to the 0 point on the x-axis. So it functions like our y-axis for this graph. Also note that we can run a best fit line even when the independent variable is dichotomous like this. And as it turns out, the line will pass through the mean of the 0 group, and on the other end, it'll pass through the mean of the group coded 1, which is the statistics tutoring group. And in this situation, we can calculate the slope of this line And the run of our line is quite easy to determine because the difference between 0 and 1 is just 1. So we know our run is 1. And using some horizontal lines, tracking those over to the y-axis values, we can identify the difference between these 2 points as our rise, indicated here by the brackets. And just, eyeballing that difference in the bracket, it looks like that rise might be 11 points. So calculating the slope of this line, rise over run, we're just computing 11 over 1, or 11. This corresponds nicely to the regression output for this particular model, where we saw that the effect of tutoring was 10.53 points. And again, that effective tutoring is just the mean difference between the groups who did tutoring and did not. And that, of course, is confirmed here by the scatter plot. Another thing that we might point out is the intercept, which is this constant row. And that 78.93 is an estimate of the dependent variable mean when the independent variable mean, when the independent variable is 0. Well, when the independent variable is at the level of 0, that means there was no tutoring. So the estimate of the intercept or constant is really an estimate of the average final score for these students who did not do tutoring, as indicated in the graph. And as we check our descriptive statistics later on in the module, we can check this 78.9 value and check that against what the descriptive statistics say in terms of the average final score for the non-tutoring group. So why don't we go back into SPSS and do just that? Let's go back and run descriptive statistics on the final score dependent variable, grabbing the means, standard deviations, and sample sizes along the way. And let's look not at overall statistics alone, but also disaggregate by key student characteristics. So a quick and easy way to get overall and disaggregated descriptive statistics is to use the Analyze Compare Means menu. So once inside the Compare Means menu, as before, I'm going to identify the variables of interest and move them into the desired box. For the sake of these disaggregated descriptive statistics, I'm interested in final score and pre-score, so I'm going to highlight those and then move them using my right-hand arrow button into my dependent list box. And then once your desired dependent variables have been moved into the dependent list, go ahead and identify a number of different student characteristics to disaggregate those descriptives by. And you see I've selected these 5 variables on the left, and I'm going to move them into my layer 1 of 1 box using my right-hand arrow button. And once you've migrated your student characteristics of interest over into the layer 1 of 1 box, go ahead and click OK. Once you've clicked OK, you should have in your SPSS output a set of disaggregated descriptive statistics, like the ones you see on the slide. For the purposes of this discussion, I'm going to highlight the table in the middle that disaggregates final score and pre-score by the tutoring variable. So here again is that table that provides disaggregated descriptive statistics for the final score and pre-score values disaggregated by tutoring. And if we look here in the table at the mean final score for the people who did tutoring, coded as 1, versus folks who did not do tutoring, coded as 0, we see a mean difference of 10.54 points. And like on the previous slide, here is the regression output for this model, which is doing the very same comparison. Note also that that constant row in our coefficients table is really just the B0 of that model. And the 78.93 that we saw in that regression, the red arrow points to the average final score of the no tutoring group. So this is just confirmation of our interpretation guidance that the intercept of the regression model is an estimate of the dependent variable mean when the independent variables are all zero. In this case, when there's no tutoring. And that's indicated there with the red circle. Also, the tutoring effect is our B1 slope in the model. And there's our 10.533 that we saw in the previous slide, and it's mapping very well to that mean difference in final score between those who did tutoring and those who did not. Let's take a minute now and review how to interpret regression elements when we have binary independent variables. In particular, when we're regressing using a continuous dependent variable and a binary categorical independent variable. So the intercept value, B0, it's an estimate of the mean dependent variable value when the single independent variable or all the independent variables are equal to 0. In the case of a binary categorical independent variable, it's going to be the estimated mean dependent variable for the group of folks who are coded as 0 on that binary variable. And we call that group of folks the reference group. Now to the slope. The slope coefficient, B1, it'll always be at the highest level, the estimated change in the dependent variable for a 1 unit increase in the independent variable. In the case of a categorical independent variable, that 1 unit difference is just moving from one group to the next. You're going from the group coded 0 to the group coded 1. So then that increase across that 1 unit difference is then the estimated mean difference in the dependent variable across those two groups. As you would expect, some categorical variables of interest have 3 or more levels. So what do we do then? Well, in regression analyses, we can handle this situation using something called indicator coding. You may also hear me or others refer to it as dummy coding. And what we do is we convert a multi-category single variable, maybe it's 1 to 5, and we convert that into a series of individual variables, each comparing a category of interest to all the other categories. So for example, let's say I had 3 people in a very small data set. I had 1 Democrat, 1 Republican, and 1 independent person. So they all receive a different value on the political affiliation variable, a 1, a 2, or a 3. But in an indicator coding scheme, what we do is set up a code that compares an individual to everyone else. So if you look at the Democrat underscore IC variable, the person who is the Democrat, person 1, has a 1 in that column for Democrat IC, but has a 0 in the Republican IC and a 0 in the independent IC column. Likewise, person 2 is a Republican, so they only have a 1 in the Republican column and a 0 everywhere else. And the independent person only has a 1 in the independent column and a 0 everywhere else. So to sum up, for any individual, there is a 1 in one and only one category, and they have zeros in all the other columns. In our practice data set, we have 2 sets of these indicator variable schemes. One set corresponds to race and ethnicity, and another corresponds to a student's College of Education program affiliation. So looking at the variables here, we can see that each student has an indicator code for whether they're in counseling, teaching and learning, or leadership as programs within the College of Education. And as you can see, if you look closely, that each student has a 1 in one and only one of these three columns. And as you look through the data set, you can find the variables that are part of an indicator scheme because those variables will have an underscore IC in their variable name. So how can these indicator schemes be used in regression? Well, we can specify regressions such that they will compare the dependent variable across categorical independent variables that have 3 or more groups or levels. The approach is as follows. If we have 3 categories and thus 3 indicator code variables, we only need to put n-1, or in this case 2 of those variables, in the regression model. Then whatever omitted category or omitted group, whatever that group is, they become the reference group by default. And when the regression is run and the coefficients are generated, those coefficients will compare the dependent variable means between the indicator group and the reference group. That is, the mean of the indicator group minus the mean of the reference group. So let's go ahead and run a regression that utilizes an indicator code scheme. As you can see on the screen, I'm attempting to regress the final score on the indicator code for teaching and learning and the indicator code for leadership. Now, I've left out the counseling program, which means that my coefficients are going to compare means between teaching and learning and counseling and leadership and counseling. And notice up here in the linear regression box that I've moved both of those indicator codes into my independent variables box. Having run this regression, let's compare our output to descriptive statistics. Again, there's our model on the bottom. Here's the regression output that you should have obtained from running that model. And here is a set of descriptive statistics disaggregated by College of Education program with the mean final score provided there in the mean column. I want to draw your attention to the intercept. The model is estimating the intercept to be 79.58. And that is exactly the mean of the counseling group. So this is consistent with our interpretation that when you run a model with indicator codes, the intercept estimate is an estimate of the mean dependent variable for the group that is a 0 on all independent variables. So if you're in counseling, you have a 0 on the TNL variable and you have a 0 on the leadership variable. So you're 0 on anything. So that says to me that the intercept must be the mean of the counseling program. And as you can see from these estimates, it's nearly spot on. Moving on, let's look at our B1 slope. It appears to be small, 0.194 difference. Let's compare that to the difference in the descriptive statistics between the counseling and the teaching and learning program, which is 0.2. So that estimate from the regression is matching the descriptives quite well. And then finally, our B2 slope is 15.19. And we have a comparison between leadership and counseling. That is 15.2. So that is confirming that our coefficient for leadership is an estimate of the mean difference in final score between leadership and counseling. Now, one thing to note before leaving this is both of the slopes B1 and B2 are positive because both the teaching and learning and the leadership students have higher final scores on average than do counseling students. If we had used leadership as the reference group, we might get a much different story. So why don't we do just that? If we were to run a regression with a different reference group, we would approach it the same way, only we would change what variables go in the model. Here, as you can see, I have now counseling and teaching and learning in the model. So by omission, leadership is the reference group. Okay, so now the model looks like this, with the counseling indicator code and the teaching and learning indicator code in the model. The resulting regression output and corresponding descriptive statistics look like this. And as you can see, the coefficients for counseling IC and teaching and learning IC are both around -15. Compare that to the mean difference between each of those programs and leadership. They are both about 15 points lower on average. Also note that the constant of this new model, the intercept of this new model, is 94.77, rounds up to 94.78. Compare that to the mean of the leadership group, which in this model was the reference group. I'd like to spend a little bit of time now talking about the role of grand mean centering and independent variable in regression modeling. Sometimes it's helpful in regression to center a variable on its grand mean. And the reason might be that we want to change the interpretation of the intercept into something more meaningful. We may want to allow for better interpretation of models, especially those with interactions. The process is pretty simple. We simply compute the mean of the independent variable, and we do that regardless of the measurement level. And then we create the centered variable by subtracting that grand mean from each of the raw values. So for example, if we had a small data set with just 2 people in it, 2 cases. One person had an independent variable value of 1 and the other 3. Well, the mean of that independent variable is 2. So for each person, we would subtract from their raw value that mean of 2. So for person 1, 1 minus 2 gives them a mean centered value of -1. And for person 2, subtracting that mean gives them a grand mean centered variable value of +1. And that's all there is to it. In your data set, you'll notice that some of the variables have an _C in the variable name. That just means that those particular variables have been centered on their grand mean. And as you look down those variables, you'll notice that some of the values are negative and some of them are positive. And that simply means that some of the raw values were above the mean and some of the raw values were below the mean. So to explore the impact of centering on a regression model, let's first look at the graphical impact of centering. So in your chart builder, if you navigate back to the scatter dot menu and again pull the final score into your y-axis variable slot, but this time pull in the centered value of pre-score as your independent variable on the x-axis. Once you've done that, click OK. Okay, so let's examine the effect of centering from a graphical perspective. Here's our old scatter plot of final score versus pre-score. And here's our new scatter plot of final score versus the centered version of pre-score. Centering is just a linear transformation. Notice that all centering did was to slide the data points to the left so that the points now hover around the y-axis. And in fact, we can see that the y-intercept of the line now has a different interpretation. And as you follow that horizontal line across to about 85, that tells us that the regression line intersects the y-axis at the overall or grand mean now of the final scores. So that's a much different interpretation than in prior analyses we've done, where the intercept was the average dependent variable for a specific reference group. Now in the centering situation, it's the overall dependent variable mean of everyone. But the other thing to notice is that although the intercept has changed, the slope is completely unchanged by the centering process. And we should also test this effect statistically by running the linear regression. Notice how I'm setting up here in the linear regression box a regression of final score versus the centered version of pre-score. Let's compare the regression results across models with centered independent variables versus models with uncentered independent variables. Here is our centered version of our model, regressing final score in the centered version of pre-score. And there's the regression I just ran. And we have run prior analyses that looked at final score versus the uncentered version of pre-score, and recall these results. And I also have the descriptive statistics, overall descriptives, for the final score variable. And I want to draw your attention to the mapping between the intercept of the centered model is 84.2 and the overall mean of final score for the entire sample. And you see that those match exactly. In addition, I would like to draw your attention to the slopes of pre-score versus final score. Notice that regardless of centering, that slope does not change. So let's review the effect of different coding schemes on the intercept of the model. We saw previously that when we dummy code, the intercept is the estimate of the mean outcome for the dependent variable for the reference group. However, if we grand mean center all the independent variables, the intercept now becomes an estimate of the overall grand mean of the dependent variable for everyone. But regardless of the coding scheme, the slope in front of the centered or the uncentered variable remains unchanged. So most of what we have done in the module so far are simple regressions that involve one dependent variable and one independent variable. I now want to talk specifically about multiple regression. And multiple regression is an extension of these simple regressions, but now we're going to involve more than one independent variable and oftentimes quite a few independent variables. Algebraically, the model just becomes y, your dependent variable, as a function of 1 through k independent variables. And as a result, if we have 1 through k independent variables, we will have b1 through bk regression coefficients associated with those independent variables. And what this allows us to do is to isolate the unique contribution of a single independent variable, having controlled for the effects of others that may be confounding our interpretation. So the focus then in multiple regression becomes on the predictive power of a combination of independent variables on a dependent variable. So let's talk a bit more about this idea of controlling for confounding variables. Here is the bullet that I pulled over from the previous slide where I indicated that multiple regression allows us to isolate the effects of independent variables uniquely, and that helps us with confounds. Let's talk about an example in your data set. We saw that the effect of tutoring on the final score was about 10 points in favor of those who went to tutoring. Now, what if we wanted to be more confident that that difference was due only to whether a student attended the tutoring or not? We might wonder, for example, what if the students who went to tutoring, already had higher scores on the pretest, right? And maybe that difference that we're seeing is more about the pretest than it is the tutoring. That is, students are coming in high on the pretest and therefore are high on the post-test as well. So if we look at these descriptive statistics again, we saw that on pre-score, the difference between tutoring and no tutoring was 6 points. So it is the case that the tutoring students came in at a higher pretest score already than the no tutoring students. Perhaps that could have confounded our estimate of the true effect of tutoring. So what would make you more or less confident in that 10-point difference that we estimated? Well, one thing that we could do is we could run a multiple regression that allows us to estimate the effect of tutoring again, but only this time control it for the pretested differences that existed. So specifically, what we can do through a multiple regression is estimate the effect of tutoring on the post-test and do so as if the pretest means had been the same in the tutoring and no tutoring groups prior to the course. So I'd like to explore with you from a graphical perspective what happens when a covariate such as the pre-score is added to a multiple regression model to adjust out any existing biases to the effect of tutoring that exist because the tutoring students came into the course already having higher pretest scores, and thus perhaps coloring how we would think about the effect of tutoring, knowing that there was already a pretest difference prior to the course. So what I have here is something that looks very similar to the scatter plot that we've been looking at, only this is a grouped scatter plot where the different colored dots are essentially disaggregations of the data by whether the students attended tutoring or not. And what we can do is we can draw best fit lines color-coded. For example, this is the best fit line through the red dots only, and this is the best fit line through the blue dots only. And in the case of the simple model that we ran to estimate the effect of tutoring, what happens graphically in the regression is that there's an estimate made of the average of final score for the students who attended tutoring, and we can see that graphically just by extending a dashed line over from the middle of the red line, and then of course we can repeat that for the blue line. And then over at the y-axis we can see where those dashed lines cross, and for the tutoring group it looks like it crosses at about 89, and for the non-tutoring group around 79. And the distance between those is of course about 10 points, and that corresponds pretty well to what we saw when we ran this regression formally in SPSS, where the effect of tutoring was estimated to be at about 10.5 points. So now let's explore what happens graphically if we go ahead and add the pre-score to the regression model to adjust out any biases for those pre-existing differences on pre-score. So what I'm going to do here is just from the middle of the blue line, indicating the average pre-score of the no tutoring group, I extend that line down and I see that the average for the no tutoring group is about 74. That's their average pre-score. And I can do the same for the students who attended tutoring. And I can see that there's a difference there at baseline of about 6 points. And when we add pre-score into the model, like what I've just shown here, what happens graphically is that the lines are extended back, and the difference, instead of it being estimated as it was in the naive model as 10 points, now what we're doing is we're estimating the difference between the groups at a new location that has the pre-score advantage factored out. And indeed, it's happening right here at the y-axis, And when you make the comparison between the groups here, you see that there's only a 4-point difference on the final score as opposed to 10. So what's essentially happening is we're taking the naive effect of tutoring, which was 10 points when pre-score was not factored or controlled for. And we're subtracting out that pretest advantage of 6 points. And we're arriving at a less naive estimate of the effect of tutoring, which does not have the pretest advantage in there. And of course, that estimate is now 4 points. So let's go ahead and run this model in SPSS. You can see in the linear regression menu that I have final score loaded as the dependent variable, and I have both tutoring and pre-score loaded in my independent variable box. So if we grab some of our regression output from that regression run, and in particular grab the coefficients table from the output, and I've provided it here on the slide, we can see that our effective tutoring, B1, that estimate is 4.16, which corresponds very closely to our just naked eye estimates from this graphical look at what happens when pre-score is added to the model. So I'd like to do now some direct comparisons between our model that regressed final score on tutoring and then the larger model that regressed final score on both tutoring and pre-score. So there was our initial simple model, and recall these were our results from that simple model. And then when we added pre-score to the regression model, we got these results that I showed you on the previous slide. And we can directly compare what happens once pre-score is added to the model in terms of possibly new interpretations of the effect of tutoring. So for example, in the simple model, we estimated the difference in mean final score between the tutoring groups and the non-tutoring groups to be 10.5 points. Whereas once that effect had been controlled for baseline differences in pre-score, the new estimate is down to 4.16 points. That alone may change our assessment of how effective the tutoring was. But we can also see that while the tutoring effect in the simple model was statistically significant at the 5% significance level, once it had been controlled for pre-score in the second model, now the tutoring effect is non-significant at the 5% level. So the addition of covariates can make pretty significant differences in the interpretation of the importance of different effects. Now that we have output for this model that includes both the tutoring variable and the pre-score variable, let's use this output to build a prediction equation that would allow us to predict the final score of any student if we knew, one, their pre-score, and two, whether they attended tutoring or not. So again, here's our output from that model that includes both tutoring and pre-score. And as a reminder, in our unstandardized coefficients column, our B column, we have these three estimates of interest. One is the intercept B0, the second is the coefficient for tutoring B1, and the coefficient for pre-score B2. So we can use our regression equation for prediction just by using those three parameter estimates, B0, B1, and B2. So for example, if a student attended tutoring and had a score of 40 on the pretest, that is enough information, given what we now have in our model, to predict what their final score might be. Notice how in this next version of the model I have the intercept value plugged in, 1.97. I have the coefficient for tutoring, which is 4.17, rounded to 2 decimal places. And that is multiplied times 1 because the student attended tutoring. So their code for tutoring is 1. And then in the final term of the prediction model, I have 1.04, which is the coefficient, B2, for pre-score. And then I plug in that student's actual pre-score. And then from that point forward, it's just arithmetic. We see 4.17 times 1, 4.17, and 1.04 times 40 is 41.60, yielding our predicted score. So what this is essentially saying is if a student had a pre-score of 40 and attended tutoring, we would predict that their final score would be just under 48 points. Before we go further with additional regression models, I think it would be good for us to pause now and just return to a fundamental concept around multiple regression. And that is that, like many statistical tests that we encounter, there are certain assumptions that need to be in place before we can feel confident about the results we're getting from that test. Multiple regression is no different than some of these other tests, and of course it has assumptions. And as it turns out, multiple regression assumptions that we want to satisfy have primarily to do with the characteristics of the residuals. Recall that the residuals are just these errors in prediction. We can think of them on the graph as the distance between the actual data point in the circle there and the predicted value, which is given by the regression line. So quickly, here are some of the assumptions that we make about the residuals in multiple regression. First is that the mean of those residuals are 0, that the residuals are independent of one another, that the residuals are not strongly correlated with any of the independent variables, that the variance of those residuals is constant across all values of the independent variable. That's called homoscedasticity. That the residuals are normally distributed, and that the residuals are linearly related to the predicted outcome scores. Fortunately, there are certain plots that we can make of the residuals, which will tell us a lot about whether those residuals meet key assumptions. On this slide, I have a plot of standardized versions of our residuals on the y-axis versus standardized versions of the predicted values on the x-axis. And we can look at this plot and look for certain characteristics that will help us test key assumptions. The first is that if we look at the horizontal line that goes through 0, we can see that it cuts generally through the middle of the scatter plot so that there is roughly an equal number of points above and below the line. So this indicates that the residuals are centered on 0 and that the mean is approximately 0. Also, if we look at the density of the points, so that means the number of residuals in any given space, that density is largest right around that 0 horizontal line. So that higher frequency around that 0 line is indicative of normality. Moving along, we can also look at the vertical spread of these residuals at various points along the x-axis. And we can see that the vertical spread is roughly the same as you move to different locations on the x-axis. That constant vertical spread, approximately, is indicative of constant variance and homoscedasticity. Next, we can see that that 0 line, which as it turns out is the best fit line through these data points, is linear. And with regard to this assumption, we can withstand small departures from linearity in this graph as long as it's not clearly nonlinear. And then finally, as a simple and quick approach to inspecting these scatter plots, if we see a rectangular shape, and if you can envision a rectangle fitted around these cluster of residuals, if you see a general rectangular shape, that suggests right away that we have good evidence that we've met the assumptions of linearity, normality, and homoscedasticity. And now that we've seen an example where the assumptions of regression around the residuals were generally met, let's look at a few examples that are clear violations. On this slide, we see a clear violation of the assumption of linearity. And on this slide, we can see a violation of the assumption of normality, as if you look at the density of points around 0, those residuals are much more sparse around 0 than they are out at the either upper or lower extremes. And finally, this is an example of a clear violation of the assumption of homoscedasticity, because as we inspect the vertical spread of the residuals at various points along the x-axis, we see that that vertical spread varies widely depending on where you are on the x-axis. So what I'd like to do now is show you how to generate these plots that will allow you to test regression assumptions. So we'll start with our normal routine of running a regression by selecting Analyze Regression Linear. And in this example, I'm going to regress final score versus pre-score. See that those two variables are loaded in the dependent and independent variable boxes, respectively. And I'm going to specify some tests for assumptions using the Statistics button. Note here in the Statistics menu that I have a number of options checked, notably the collinearity diagnostics. Once you have checked those boxes along with me, go ahead and click Continue. Now I would like to specify a few things that will allow us to test assumptions, and I'll do that through the Plots menu. And then once in the Plots menu, we can construct that scatter plot that we have been analyzing for assumptions tests. So how to begin is to locate the zpred variable, which is just saying the standardized predicted values. We're going to load those on the x-axis. And then locate the zresid variable, which is just indicating that we have standardized residuals variable, and we're going to load those onto the y-axis. Also, let's go ahead and check our histogram and normal probability plots. So then once you have done that, your screen should look like this, with the histogram and probability plots checked. And when you're ready, you can click Continue. And at that point, you will be returned to the overall linear regression menu, at which point you can click OK. So in your regression output, you'll find this scatter plot of regression standardized residuals versus regression standardized predicted values. And upon inspection, we could make a number of arguments about whether our residuals meet certain assumptions, and it looks like certain assumptions it would be hard to defend that they have been met. But I just want to flag that it's really hard with a small sample size to interpret these plots, and we need to do so with caution. And that's because the small sample size makes the patterns less discernible and really subject to the effect of outliers, where one or two residuals might really change the shape of this distribution of points and cloud our assessment of whether the assumptions have been met. So I'm going to leave this discussion of assumptions assuming that for the educational purposes of this module, that we have met these assumptions sufficiently to move on. But now you know how to make such a plot so that when you're doing research with presumably larger samples in the future, you at least know how to create the required scatter plot and then interpret it for whether assumptions have been met. So again, we will assume that the assumptions were met sufficiently and we will move on. One other consideration of note, especially for multiple regression analyses where there are multiple independent variables, is this idea of multicollinearity. Multicollinearity is a concern we have when our independent variables are highly correlated with one another. And the problem with it is it can make our regression coefficients volatile to small changes in the model. So the values of those slopes and coefficients can change quite a bit just by adding or subtracting maybe one other variable to or from the model. And that volatility can decrease precision in the regression estimates, and ultimately that could lead to incorrect conclusions about statistical significance. So how can we test for this? Well, you may have seen in some of the model specifications that I've done in SPSS where I've checked the collinearity diagnostics box within the regression menu. Well, that's essentially how you run multicollinearity tests. And I'll return now to SPSS to review how that is done. So to review, I would like to test multicollinearity for a model, a familiar model, where we have tutoring and pre-score as independent variables predicting final score. So as you can see, I'm in my linear regression menu here. If you want to follow along, I've loaded final score as my dependent variable, tutoring and pre-score as my independent variables. And now I'm going to click on statistics to access the multicollinearity information. And within the statistics menu, to make sure that we get multicollinearity information with our regression output, we just need to make sure that we have the collinearity diagnostics box checked. Let's look at our multicollinearity results. SPSS puts the multicollinearity information in the coefficients table. So you can see over here in the far right of our coefficients table, we have collinearity statistics, namely the tolerance and the variance inflation factor, VIF. And really, tolerance and variance inflation factor are two sides of the same coin, where tolerance is just the reciprocal of the variance inflation factor. And you can see that in this case, the tolerance of 0.927 is just equal to 1 over 1.079. So how much is too much when it comes to multicollinearity? Many statisticians believe that you have too much multicollinearity, your independent variables are too highly correlated if your tolerance is less than 0.2, or if your variance inflation factor is greater than 5. So in this case, we would conclude using these cutoffs that we do not have a multicollinearity problem where tutoring and pre-score are too highly correlated to be in the same model. Now that we have spent some time testing regression assumptions and looking at multicollinearity diagnostics, I'd like to return to regression modeling by introducing some new terminology that's going to be helpful down the road. And the first term I'd like to introduce is main effects. A main effect is an overall effect of an independent variable on a dependent variable that does not depend on the level of any other variable in the model. So let's go back to our familiar example of final score as a function of tutoring and pre-score. And recall these were the results that we just saw when we run that regression model. B1 and B2 are considered main effects, and that's because B1 is the overall effect of tutoring on final score, and it's not dependent on the student's pre-score. Similarly, B2 is the overall effect of pre-score and final score, and it's not dependent on whether the student attended tutoring or not. On the other hand, sometimes in regression modeling, we're interested in interaction effects. An interaction effect is an effect of an independent variable on a dependent variable that does depend on the level of another variable. And in the literature, sometimes you will see that interaction effects are also called moderator effects. So an example would be, what if we were interested in the following question? Does the effect of tutoring on final score depend on whether the student completed the study questions assignment? This particular question can be addressed by testing the interaction between the tutoring and questions variables. However, before we look at this interaction from a regression standpoint, let's first look at it descriptively. And how we'll do that is in SPSS, we will use our Analyze Compare Means menu. And once in the means menu, notice that I have loaded final score into my dependent list. And using the right-hand button, I have loaded the questions variable, the non-centered questions variable, into my layer 1 box. And now I want to add a second layer of disaggregating the means, and I'll do that by using the next button. And then once in my layer 2 menu, notice that I've used the right-hand button to move the tutoring variable into layer 2 of 2. And once I've done that, I want to specify some options that are going to simplify my tables. So under the options menu, when I click that, then I get this other box off to the right that's called means options. And notice that in that menu, I've specified that the only cell statistic I'm interested in right now is the mean. And once I have selected mean, I click continue. And clicking continue from the options box should bring me back to the general means menu, at which point I can click OK. What I've put on the slide now is one of the tables that you should have been given in your SPSS output from that compare means menu. And there's a lot that we can learn just by comparing the means across these different disaggregated groups with regard to main effects and interaction effects. So for example, the two numbers at the end of the bracket, those are the overall means for the final score for students who either completed the study questions or did not. So that's the overall effect of doing the questions, which is 92.50 minus 74.41, or 18.09 points. That's the overall effect of questions. Likewise, elsewhere in the table, we can see the overall means on the final score exam for students who either attended tutoring or did not. And we can see the difference in those two means, which is the main effect or overall effect of tutoring, to be 10.54 points. And we've seen that effect in other analyses that we've done earlier in the module. But there are other comparisons that we can do just within this disaggregated means table that will illuminate what the interaction effects might be. So for example, if we compare the effect of tutoring just within the group of students who completed the study questions, as indicated by this blue bracket, we see the effect of attending tutoring for the non-study question group to be about 14 points. And down here, we can see that the effect of tutoring for the students who did complete the study questions to be about 7.5 points. So one way to look at this is that the effect of tutoring, if you do the study questions, is 6.5 points smaller. So tutoring is less effective if you already do the study questions. So that is an example of interpreting an interaction effect, because clearly the effect of tutoring does depend on a third variable, and that third variable is whether or not you completed the study questions. In addition to looking at main and interaction effects by inspecting descriptive statistics, we can also learn a lot about those types of effects from a graphical standpoint. So what I've revealed on the slide is a screenshot of the chart builder menu, where I've accessed that from the graph pull-down menu. And in the chart builder, I'm going to create an interaction graph that is set up for use with categorical variables. And what I'm going to select here is the line menu, and in particular the multiple line type of graph. And we can drag that up into the preview window. And once we've done that, we can select the final score variable from our variables list, drag that to our y-axis, then grab our tutoring variable and drag that to the x-axis, and then finally grab our questions variable and drag it to the set color box. So in your SPSS output, you should have a line graph similar to this. And I've cleaned mine up a bit, just removing some extraneous information for clarity. But I think that we can inspect these graphs and learn a little bit about the interaction effect. So let's start by looking at the green line, which is the line for the did complete study questions group. And I've entered a vertical bracket here as the vertical rise of that line that looks like it goes from just under 90 to just over 95, and perhaps that distance is a vertical rise of about 7.5 points. And likewise, down on the blue line, it looks like over the run of that line, it has a vertical rise of about 14 points. And the run of both of these lines conveniently goes from 0 to 1, because that's the coding of did not attend tutoring and did attend tutoring. So that run is conveniently 1. So we can think of, with regard to the blue line, as this being the final score versus tutoring slope for the no study questions group. And that slope is just going to be the rise of 14 over the run of 1, or a slope of 14. And similarly, the green line is the slope of final score versus tutoring for the group of students who did the study questions. And that slope is a rise of 7.5 over a run of 1, or a slope of 7.5. So when we look at the difference between the two slopes, notice how we get 7.5 minus 14, negative 6.5. It's very similar to what we saw in the descriptive statistics. And in fact, that is the graphical interpretation of an interaction effect, is that it is the difference between the two slopes. Specifically, that regression coefficient is the slope of the indicator group. In this case, it's questions equals 1 group, minus the slope in the reference group, or the questions equals 0 group. And again, that's negative 6.5 points. So in addition to examining interactions both through descriptive statistics and graphical approaches, it's also important to formally test interactions using our multiple regression modeling techniques. I'd like to spend some time on this slide talking about how to set up an interaction test in multiple regression. So it is often best to use the centered variables in models that contain interactions, and that's because we want to be able to run models that contain interactions and still be able to interpret the main effects as main effects. So what we do is we create a multiplicative interaction variable, and we do that by finding our two centered variables and creating a product of those two centered variables of interest. And in this case, it's the centered version of tutoring and the centered version of questions. So for example, if we had 3 people in our data set, and we can see that they have a centered value for tutoring and a centered value for questions, we would just multiply horizontally across those rows to come up with that column on the far right, which is the product of those two variables. And then we would add the interaction variable to the model. So now the model would become final score as the dependent variable as a function of our main effect of tutoring, our main effect of questions, and then the interaction between tutoring and questions. And from this model, we'll get a B3 coefficient. And that B3 coefficient will tell us how much different the effect of tutoring is on final score when the students do the study questions as compared to when they do not. So to specify this model in SPSS, we will use our normal linear regression menu. Notice that I have put final score in my dependent list, and in my independent list, I have questions centered, I have tutoring centered, and then I have the multiplicative product, which is my interaction variable between tutoring and questions. Now let's look at some regression results and compare those results to what we had already suspected from looking at either the graphs or comparisons of the descriptive statistics. Here's our model again. We knew from just comparing descriptive statistics that the main effect or overall effect of questions should be around 18 points in favor of the students who did the questions. Now, here is the output from the interactions model we just ran, and we see that the coefficient, which would be B1, or excuse me, B2 for questions, is 17.78, which is approximately 18 points. Likewise, we found from comparing descriptive statistics that our main or overall effect of tutoring should be around 10.5 points. And we see that is also true in our regression output. And we saw from comparing the slopes of the graphs that the difference between the slope, when we subtract the indicator group minus the reference group, that difference should be negative 6.5 points, and the difference in the slopes. And that is being, again, confirmed in our regression output for B3, which is the interaction effect. And just one other thing to notice is that we grand mean, all the variables in this model are grand mean centered, which means that our intercept should be the overall mean of the dependent variable, which is final score. And we saw in our descriptive statistics that grand mean of all the final scores, regardless of group, is 84.2, and then that's being, you see, estimated again by the intercept of the model, B0. I'd like to continue on with our regression output for the interaction model with some additional substantive interpretations. Again, here are our results. And we see that the effect of doing the study questions is statistically significant, controlling for the effects of tutoring. We also see that the effect of tutoring is statistically significant, controlling for the effects of doing the study questions. And recall that we had an interaction question in here as well, and that was, does the effect of tutoring on final score depend on whether the student completed the study questions assignment? And we saw that the effect of tutoring is 6.5 points smaller for students who complete the study questions. But we also see that that interaction effect is not significant. But we need to acknowledge in this particular situation that the sample size is quite small in this practice data set. So we don't have a lot of power. So the non-significance of that effect could very well be linked to small sample size, where that difference in slopes of negative 6.5 points might very well be significant in a larger study. It is also possible to test interactions between continuous and categorical variables. For example, what if we were interested in the following research question? To what extent does the effect of comfort with statistics on final score depend on whether the student attended tutoring? To test this question via an interaction, we would specify a model such as this, where we have final score as our dependent variable. Notice that we have the main effect of tutoring and the main effect of statistics comfort. And then as our final term, we have the multiplicative interaction between tutoring and statistics comfort. But before running that model, we can first look at the situation graphically. In our chart builder menu in SPSS, if you go to the scatter dart menu and select the scatter plot and drag that to the preview window, then you can select final score and migrate that to your y-axis, stat comfort and move that to your x-axis, and then moving your tutoring variable to the set color box. Also in SPSS 27, I can tell SPSS to fit a regression line for each of the individual groups, the tutoring and no tutoring groups, by checking the subgroups box. Now this is a little bit of a key difference between SPSS 27 and 26. I'm showing SPSS version 27 here. If you're using 26, over to the left you will have a grouped scatter plot option in addition to just the plain scatter plot option. And you would want to select that instead and drag that to the preview window. And then you'll have options from there to get these fit lines estimated at the subgroups. But this is how it looks in SPSS 27. So in your SPSS output from the chart builder, you should have a graph that looks somewhat like what I have in the middle box under Chart Editor, where I have two best fit lines drawn through the points, and the two lines correspond to the two groups, tutoring and no tutoring. And if I double click on the lines themselves, the properties box will open up, and I can select fit line, and then additionally I can check the box for attach the label to the line. And what the label actually ends up being is the individual regression models that go with the individual lines. So on this slide, I've transferred that scatter plot and simplified it a bit, but here it is again with both the best fit lines and the regression models that go with each line. And I want to point out the information that we can get from those individual regressions. So for example, this is indicating that the slope of the green line, which is the indicator group, they attended statistics tutoring, that slope is 6.99. And that the slope of the reference group, who did not attend statistics tutoring, the blue line, that slope is 10.7. So if we recall our relationship here is that the interaction effect is the difference between the two slopes, and specifically it's the slope of the indicator group, and that's the tutoring equals 1 group, minus the slope of the reference group, which is the tutoring equals 0 group. And we do the arithmetic, we see that that interaction effect is negative 3.71, indicating that the relationship between statistical comfort and final score is weaker for the group of students who did the tutoring. And now that we've investigated the interaction between tutoring and statistics comfort graphically, let's go ahead and formally test that interaction using the linear regression menu in SPSS. Notice that I have final score as my dependent variable, and I've loaded in my independent variables box the centered version of the tutoring variable, the centered version of statistics comfort, and the multiplicative interaction between those two centered variables. And here we have the results of that regression model. Let's spend some time interpreting them. We see initially that stat comfort is a significant predictor of final score. And it has a coefficient of 8.8, which means that for every 1 unit increase in stat comfort, the model is predicting an 8.8 point increase in the final score. We also see the effect of tutoring is much smaller than in some of the other analyses we've done, where statistics comfort was not controlled, We saw in some of the other analyses that effective tutoring was as big as 10.5 points, and here we're seeing it estimated at 5.4 points and as non-significant. And also, we can see that the relationship between stat comfort and final score is 3.71 points weaker if you do attend the tutoring. So that directly responds to our original interaction question, where we were asking, to what extent does the effect of comfort with statistics on final score depend on whether the student attended tutoring? And it looks like to some extent it does depend on whether the student attends tutoring. Let's now take a few minutes and review what we've learned about regression parameter interpretation. Let's start with the y-intercept. The graphical interpretation of the y-intercept is that it's the place where the line crosses the y-axis. And if we're running a model with independent variables that are indicator coded, the intercept is the estimated mean of the dependent variable when all independent variables are set at 0. Whereas if our independent variables are grand mean centered, then the intercept becomes the estimated mean of the dependent variable. As for the coefficients, the graphical interpretation would be that the coefficient is the slope of the best fit line through a scatter plot of the dependent variable versus the independent variable. And in the most general sense, you can also think of it as the estimated change in the dependent variable for a 1 unit increase in the independent variable. And then there are special cases where we want to interpret coefficients. So for example, if we're dealing with binary categorical independent variables, the coefficient is interpreted as the estimated mean difference in the dependent variable across the binary coded levels 0 or 1. And if we have a categorical variable with 3 or more categories that's been indicator coded, then our coefficients give us the estimated mean difference in the dependent variable between the indicator group and the reference group. And for an ordinal independent variable, the coefficient is interpreted as the estimated change in the dependent variable for a 1 ordered category change in the independent variable. And if the coefficient is representing an interaction effect, it's interpreted as the estimated difference between the scatter plot slopes. I'd like to take just a few minutes and close the module by comparing regression to other statistical tests. Looking at this table I provided on the slide, in the first 3 rows I have 3 tests that are very common in basic statistics, and that's the Pearson correlation, chi-square, and t-test. And these 3 tests, although very common, they're also quite limited. First of all, they're limited in the number of independent variables that are possible. And they're also limited in the type of variable that can be used as the dependent variable or independent variable. And in the social sciences, it's really difficult to model relationships with one independent variable because most relationships are very complicated, and we're always at risk in our attribution of relationship between any independent variable and a dependent variable. We're always at risk of a confound with a third variable. So not being able to have a second independent variable tested is really the main limitation of these first 3 tests. Now, the factorial ANOVA does allow for multiple independent variables, but it still has the limitation that the dependent variable must be continuous and the independent variables must be categorical. Whereas you see in the multiple regression row, not only can we have multiple independent variables, but those independent variables can be of any measurement level. And in fact, there are different types of regressions that would allow us to have any type of dependent variable either. So overall, I favor multiple regression for most of my analyses because of its flexibility in terms of the types of variables that can be specified as dependent variables, the types of variables that can be used as independent variables, and then, of course, the total number of independent variables that can be specified.